In this lecture, we'll focus on the matplotlib library, in particular the pyplot module, which is a very useful library for visualizing data. So we're going to look at how to create simple plots. Then we're going to go back to the data that we were working with in the previous lecture, Gapminder, and see how we can plot relations between different indicators, and then create an animation by automating the generation of different plots. So let's start with a simple plot. We have this file with the tuberculosis burden in Portugal, with the number of cases by 1,000 inhabitants for different years. So this is data from the World Health Organization, and this matrix has 4 columns. The first one, the year; the second one, the estimated burden; and then the lower and upper limits in the confidence interval for the estimate. So in 1990, the estimate was 91 people with tuberculosis per 100,000 inhabitants, but with this confidence interval. So we want to load this data and represent it graphically. To load the data, in this case, we can just use, we can load this directly into a NumPy array, because this is just a file with numbers. So it's easy. You can just use the load text function from NumPy, and you input the name of the file, and you get this as a NumPy array. This load text function actually has lots of different options that you can use for skipping header rows, for changing the separator, and things like that. So it's actually more flexible. There are lots of files that you can read with this function, but it's basically for files that are composed of numerical data. You just read everything into a NumPy array. Now we're going to create the plot, and to do that we're going to import the pyplot module from matplotlib, and to avoid having to write this whole name all the time we want to use something from this module, we're also going to give this a nickname, and this is the conventional nickname for pyplot, which is PLT, and you're going to find it easily if you look for examples on the internet. So the same way as NP is an often used nickname for NumPy, PLT is for pyplot in matplotlib. Now the way we're going to plot data follows basically this recipe. We create a figure. If you don't create a figure, then the first time you call the plot function, the figure is created, and then you can plot different series calling the plot function. So these will all be plotted in the same figure that you created. You can change the title, labels for the different axes, and so on. And optionally, you can use show. But this now depends on where you are running your code. I'll explain a bit better. If you are using Spider and the IPython console, even if you don't have show here, when your script terminates, the console notes that there is a plot object in memory, and all the plot objects in memory will be shown on the console and then deleted from memory. If you want to show the plot immediately, you can add the show here. So then you will show the plot in the IPython console when the show command is executed. But in this case, for this script, this will not make a difference, because show is the last instruction and you just see the plot there. However, if you are running your code outside of Spider, so running your code standalone, the show command will make the plot appear as a separate window, and then only when you close the window will your program continue. So this works differently whether you're using IPython or just your code standalone. In general, when we are automating data processing, we are not going to use show. We usually are just going to save the plot to a file. I'll show you some examples of that later. But if you run this script on Spider, you will see the plot appear on the console. And the reason why these series have different colors is because for plotting, we are using, from this data, we are using the first column for the year. So this notation here is telling Python that we want from the data matrix all the rows. This column here specifies that we want all the rows, just like when we use slicing with lists and so on. But since this array is two-dimensional and we are using a NumPy array, we can index it like this. So we want all the rows of column 0. And this is the years, what we get here on the x-axis. And we want for the y values all the rows in column 1. So column 1, remember, is the estimated tuberculosis load in Portugal. And we specify here that when we want this drawn as a single line in this color, K, which stands for black. So this is the black line that we have here. Now we do the same thing for the lower bound on the confidence interval, but we plot that in green. This is a green line here, and the upper bound in red, the color here. So basically, when you're plotting, you give the x values, the y values, and you often provide the string with formatting information, which can include the type of line, the type of marker that you're going to use, the color, and so forth. Those of you who used MATLAB before probably recognize this because it's the same format, basically. If you never use this kind of thing, it's also easy to search online for plotting, and you see the list of all these options. So I'm going to show you several examples, but I'm not going to try to be exhaustive in listing all the different options. There is really no point in trying to memorize these things. You just look up the documentation when you need or examples. So this would be the general approach when you want to automate the generation of images. This would be creating the plot, setting the title, and then using savefig from the pyplot library. This savefig function allows you to specify a file name. It will determine the format by the extension. So in this case, this is a PNG graphic format. And there are additional options. I usually set this bounding box to tight. This is the frame that you have around the plot. So if you set it to tight, it's going to be as small as possible, and it makes it easier to include the image in documentation and so forth. And this is the resolution, dots per inches. So this combined with the figure size that you can specify when you create the figure. This fig size is a tuple that has the width and the height of the figure in inches, will determine the total resolution in pixels. So you see, since you have 10 inches in width with 200 pixels per inches, you have 2000 pixels and 1400 pixels in height in this case. So this allows you to control the aspect ratio of the image and the resolution of the image so that you can fine tune it, for example, for reports, for documentation, and so forth. And this is the example, in this case, the image saved that I'm showing here. You can choose different representations. So these are just examples. I advise you to look up the documentation if you want to see more. But in this case, this is a red circle, this series here. This is a green cross, the axis there. This is a black dashed line, and you have the dashed line like this. And there are many different options that you can choose. You can set specific attributes like the size of the marker, the width of the line, and so on. There are many options here in plot that have default values that you can change. For example, here I drew a thicker line for the estimate and thinner lines for the boundaries. And you can also use different styles. I actually do not like the default style very much, so I often use this Seaborn style. So from the pyplot, you have this style module, and you can set the style that you want. There are different styles here. You can check the documentation online and see how they look like or experiment with them. But this Seaborn style is more modern, and so it looks better than this more archaic looking style that PyPlot has by default. But this is mostly a matter of taste, so you can choose your own. The idea here is just to show you what you can do. You also have different types of plot. This is just an example of using a bar plot. In the bar plot, the x values determine the center of the bar, and you will have additionally a parameter for the width of the bar in the same units that the x values are. So in this case will be in years. And so if you don't want your bars to be overlapping, you need to put some offset to your bars so that they are changed in position one relative to the other. So in this case, one is drawn in the middle of the year minus 0.2, the other in the middle of the year, and the other in the middle plus 0.2. So you get this effect here for the years. You also have different options for colors and so on. If you don't add options for colors, you have some automatic colors depending on the style that you're using. So this is the example for the default. This is an example for this other style Seaborn, and then different styles have different automatic colors. So basically, plot, you give the x and the y and and the additional parameters that you want, and usually you draw a line or just a set of points. This is for a scatter plot. Bar will draw a bar plot, and you have different kinds of plots also in PyPlot. So these are just two examples of simple plots. Okay, so now let's complicate things a bit and see one thing that we can do with automation that would be extremely boring to do manually. We're going to, sorry, not exactly. So we're going to, I'm going to give you just an example first before going for the animation. I was skipping ahead. We're going to look at these examples of simple plots, but using the actual CSV file that we can get from the World Health Organization. So look here that we have in this simple example just the data for Portugal, but if you actually go to the World Health Organization site, what you get is something that is similar to what we saw in Gapminder, but has this kind of information. So for each country, you have the name of the country, the ISO 2 and ISO 3 codes for the country. You already saw this with the example that we saw last week, where we were getting the temperature values from the World Bank site. And we have also this the year for which the data corresponds, then the population and the tuberculosis, the estimated load, the lower bound and the upper bound, and other information. So what we want here is basically we're going to identify each country by the ISO 3 code. We want it on the third column. On the sixth column we have the year, and columns 8 through 10 we have the values for the tuberculosis burden. So we're going to read this into a list with all the data, and then we're going to extract a matrix with the years that we want, the estimated burden, the bounds, and then create a function that can plot any country from this data. So we're going to use this CSV module for reading the CSV files. This is another example of a common data file. Some of you may have data in CSV files, so this would be a simple way of reading from those files. We're also going to see further on another library, pandas, that encapsulates a lot of these functionalities and actually can be useful for dealing with different types of tables and so on. But for now, we're going to look at these more simpler libraries first. And we're going to create this function that loads the data into a list of lists. And this is trivial to do with the CSV module, because that's what the CSV reader does. What we need for the CSV reader is to give it a file object from which it can read. We specify the delimiter, the character used for quoting text. For example, in this case, all the text fields are quoted by double quotes. So we specify that here. The delimiter is the separator here between the cells, which is a comma. We have a comma separated file. And we're also going to include this option here, which basically tells the CSV reader to convert into numbers values that are not quoted. So everything that is not marked as text, like these values here, it will convert into numbers. This is useful because we don't want these values as text. We want the actual numbers so that we can plot them, do any computations that we want. Okay, so this basically is the function. We open the file for reading. We give the file object to the CSV reader. It will read the file and give us an iterator that we can use to go through the CSV file row by row. If we want to return a list with all the rows of the files, then we just use this list function and convert this iterator into a list. So basically, in this instruction here, we obtain this object that allows us to go through the CSV file row by row, doing all the necessary conversions. But with this instruction, we just go through the whole file and create a list. This is useful if the file can be stored in memory. If you have a very large CSV file that cannot fit in memory, then you shouldn't do this. You should do a for loop, for example, and iterate with this object to extract the information that you need. But these kinds of details, you then, depending on the actual problem that you're solving, you can look up the documentation, see the examples, and so on. The idea here is that we are using this CSV module just to obtain a list of lists with the data. So when we load the data, we have a list of lists in which each of the elements is a list with one row. So the first element in this list is this list corresponding to the first row of the file. The second element is this list corresponding to the second row, and so on. Note that this is very convenient because everything that is text in the CSV file is stored here as strings, but those things that are not marked as text, are not quoted, were converted into numbers. So you can see that these are actually numbers and we can do computations with them. So we don't need to do manual converting like we saw in some examples in the beginning. Okay, so now what we want is to be able to extract from this table the infection rate for one particular country. So we create this auxiliary function that receives the whole table, the ISO 3 code for one country, and what it does is to go through the table, and if the third column contains the ISO code for the country, note that index 2 is the third column, and so this corresponds to this column here, which has the ISO 3 code for the country. So if this column contains the code that we want, then we're going to append to our data a tuple with the information that we want, which is the year, the estimate of the tuberculosis burden, the lower bound and the upper bound. So it will look like this. And now we can convert this list of tuples at the end into a NumPy array so that we have this in the matrix, and this is quite useful now to extract rows, columns, whatever we need. So we can test this function. Let's get the data for Portugal, and we have the matrix here with the data for Portugal extracted from this table, which contains the data for all the countries, at least that the World Health Organization provides. So now we want to plot a country. We have the table and the code, and we get the data for that particular country. We create an image and we plot the data like we saw before. So with the example we saw before, we already had everything in the matrix. Now we're just doing the previous steps to get the data for a country in the matrix. But now we have a set of functions that allows us to plot any country. So in this case, let's set the style, for example, to Seaborn, load the data and plot Portugal, and then save the image. So we can do this for Portugal, but we can do this for any country, and the only thing we need to change is this ISO 3 code, we extract the data for the country that we want and we plot it. Okay, so this was simple plotting and also revisiting this part of loading the data, structuring things in memory, extracting the data that we want, because there is a pattern here that I'm sure you noticed. This is something that you have to do very often when you're automating data processing. You have to think about how to store data in memory and then think about how to pick the values that you want and to process them to get the results that you want. Okay, so let's go a bit beyond this and automate the generation of plots in order to create an animation. And the idea is that we have different values here that we may want to relate. For example, life expectancy, GDP, population, and so on. And an animation can allows us to see this better, how they evolve over time. We're going to start with a simpler example where we're going to create a generic function to represent two series of values. One will be used for the x axis and another for the y axis, with some labels for the axis, the legend, and so forth, and by also being able to specify which axis, if any, we want in a logarithm scale. The idea is to be able to do something like this, where we can compare, for example, life expectancy of different countries as a function of the logarithm of GDP. So this is the logarithm of per capita GDP, this is life expectancy, and we can see how the countries evolved over the years, the different countries, using these indicators. So what we need to receive here is a set of labels that we have here, so the different series, the x and y values in matrices, so each column corresponds to a different country. Remember that this is the same format that we used previously, where we extract the data and we have 1 year per row and 1 column per country. So we are using these labels as the names of the countries, and the columns in these two arrays are giving us the corresponding values for each country. So now we're going to go through all these labels and their corresponding positions. The index is 0, 1, 2, and so on until the end. And we're going to plot the indicator that we want on the x value for that particular country over all the years that we have, and correspondingly the indicator we want on the y value for that particular country for all these years, and we're going to label it with the name of the country. And then we have these optional arguments here to determine if you want the x axis to be logarithmic or the y axis, and we can set that here. So we have plt x scale to set the scale of the x axis logarithm, or this one to set the y axis. Okay, so let's see how we can use this. We can load the data. Again, I'm using this Seaborn style just because I like it better. We select a list of countries, for example this, an array, a range of years, and we get the indicator GDP, population, and life expectancy. So we get these values as matrices which have each row corresponding to 1 year, each column corresponding to 1 country. So this is the get indicator values function we saw in the last lecture. And we're going to extract these indicators from the data dictionary that we have, specifying the different indicators. So now we can compute the gross domestic product per capita by dividing GDP by population. And now we can do different plots. For example, let's use per capita GDP in the x-axis, life expectancy in the y-axis for these countries using a logarithmic scale on the gross domestic product. So this would be this example here. We're seeing life expectancy as a function of GDP per capita, but putting this scale in a logarithmic. We can do this, for example, GDP per capita and population, GDP per capita and population, but with logarithmic scale on both scales. And then we have different plot. So for example, this is GDP per capita and population, and you see that you have China here with a huge population, and you can hardly see all the other countries. So if you add an option to get everything in logarithmic scale, then it's easier to see the differences. Okay, so this is an example of this idea where we create an auxiliary function to do the plot the way we want. Everything about the plot is set up here. And now we just call the function with whatever values we want, and we get plots that are consistent in their look, and they're easy to create because we don't need to be writing the code every time we need a new plot. We just use our function. And this is, again, a useful idea for automation, especially if you have to do reports with lots of charts and things like that. And it's useful to have this auxiliary function that where you fine-tune everything about the plot that you want, and then you just use it to plot whatever you need. So let's go on to the animation. We're going to use these three indicators, any three indicators, one for the x-axis, one for the y-axis, and the third for the size of the marker. And now we're going to animate the display to show how over the years we're going to move around in this space of parameters, changing the representation. So we're going to create one image for every year and then combine everything into a movie. So the first step, let's draw one frame for all the countries. We're going to create a function that draws circles using on this particular axis. So we already have the figure created. We are just going to provide the function with the plot object where it's going to draw everything. We have the values for the x-axis, the y-axis, the values for the different sizes, and all of these will have will be arrays for the different values to plot. And we have different colors. So we are going to loop through all the different colors. These will all have the same size. So if we are plotting, for example, 4 countries with 4 different colors, we will have one area of the marker for each one y value and one x value. So all of these will be arrays of 4 elements. So we're going to enumerate the colors. We have the color and the position of the color in this array. We're going to get the x value from this array in the same position, the y value from that same position. The size will be taken from the areas. Now there is one constraint here. The marker size for plotting must be an integer. So just to be safe, we convert the area here to an integer in case we were provided with fractional numbers or floating point numbers. So we convert that to an integer. And then we use this alpha. This is an additional parameter that we can use in plot for transparency. So if this is actually the opacity of the plot. If you have an alpha of 1, it's completely opaque. If you have a fractional alpha, it's semi-transparent. And we also set the color to the color that we have here. Okay, so the way we can use this is to create a figure. This GCA is get current axis, so we get the set of axes where we're going to plot things. We are going to create here a scaled version of the population. So remember that we have these arrays here: GDP, population, life expectancy, and per capita GDP. And we're going to use population for the size of the marker. The problem is that if we just use population for the size of the marker without changing anything, then China will be a huge marker and cover the whole plot. So we're going to use the square root of the population and scale it by 200, so we have a size of the marker that is more reasonable. And now we're going to draw the circles for these countries. We're going to draw the circle for row 50, just in our data, but we're going to use all the columns in row 50 for per capita GDP. This will be the x-axis. All the colors, all the columns in row 50 on life expectancy. On this matrix, with the scaled population. So remember that population is a matrix with a population for all countries for all years. When we do this, we get a matrix of the same size, but now with the square root divided by 20 for each value. And the colors we can specify, we can create different colors here for the map. For example, red, blue, I can show you here. These are red, green, yellow, and black. So these would be the colors. I am missing the actual values here, but I can show them later. And now we set the scale and the limits for the axis, and we save the image. So this gives us an example of what the frame would be. We have the per capita GDP on a logarithmic scale, the life expectancy here on the y-axis, and then the size of the marker gives us an idea of the population, and this is where each country was in this particular year that we had here on row 50. Okay, but this is just one frame. We want to do an animation, so we need to repeat this for a large number of frames, and we need to be able to specify the colors and the countries and things like that. So basically, we need to specify what the data are for X, Y, and the size of the marker. We need to specify if we want logarithmic scales on any axis, the label for the axis, the limits for the axis, and the colors for the different countries. So this will be our function. Our function will receive the years, the axis, and the colors, but the years are a vector with just the numbers of the years. The axis will be a dictionary with all this information, the data for the indicators and whether or not they are logarithmic, and the limits for the axis. And then we provide a list of colors for painting the different circles. So this is how we can create the colors. We can use names. You can create colors in many different ways for plotting. You can use names. You can use red, green, and blue values mixing together using tuples of numbers. You have many different ways, but we're going to use this simple approach here. So this is for the different countries. Green, black, orange, red. This is green for Portugal, black for Germany, orange for Spain, and red for China. And now we're going to create this dictionary, which for the x-axis, we're going to use as data the per capita gross domestic product of our 4 countries. We're going to set it to a logarithmic scale, and the limits for this axis will be between 100 and 100,000. The y-axis will have life expectancy, will not be logarithmic, will have this scale, and this is the label for the axis. And the area will just have the scaled population data, because area will not have logarithmic and things like that. So this is the dictionary that we're going to send to our function here for the axis. And so in our function, we need to use that dictionary to specify everything that we want to do. So the reason I'm showing you this way is one alternative to this would be to create a very large number of parameters here. But this can be a bit confusing, so it's easier to just have this parameter called axis, and this parameter is a dictionary with all the options we want for the axis. So now when we are plotting, we are looking at the dictionary, and when we draw the circles, this is the function that we used, that we created here. When we call this function, we go find in the dictionary what is the data to use for the x-axis, what is the data to use for the y-axis, what is the values for the area, and what are the colors to use. And these will be the values corresponding to each particular year. So we're going to loop through all the years that we have, and we're going to get for each particular year the row in this matrix that corresponds to the year. And all the columns will have the data for all the countries. So this draws the circles for all the countries in one particular year. We also set the title to be that year, so we can see the years changing over time. And we just create one figure. We obtain the axis for that figure, and for each iteration we clear the array, the graphics that are in that figure. So this CLA is something that you can call in plot to clear the current image and wipe all the series that you have there, so that we delete the previous circles and we write new circles for this year. Now we set all the limits, so we have the X limits, the Y limits, the axes that are logarithmic. We save the figure to a file, and then we repeat all of this for all the years. So this can take a bit to run because we are running through a large number of years and saving all these images. But after we have the images, we can take all the images that were generated. So note here that the name of the file will be inside the image folder, will be a series of numbers with the index of the image and then .png. So with this format, we are writing images 0000.png, 001 png, and so forth. So we are writing them in order with these numbers. And this makes it easy to then use some video editing software or just a command line to put everything into a movie. This is what I used to generate the movie. So I used FFmpeg. I'm not going to go into details into these options, but you can find the recipe if you use this program, or you can load everything into a video editing software and save it like that if you want. But if you want to really automate everything, then you just create a shell script with the command, and this creates the MP4 video, which you can see here. So this is the final result. We are seeing the different years, and then we are seeing what happens to the different countries over the years. We can see the effect of wars, of epidemics and things like that in life expectancy, and we can see how the countries are progressing over the years. So in general, you can see that life expectancy tends to increase first, and then GDP starts increasing. Note that GDP has a logarithmic scale, so this movement in the horizontal will then start to be, when it starts to get faster, it's really an exponential growth in GDP. So this is an example of how we can use the automation of generating plots to create a large number of images that then we can combine into an animation. So it's easy to do these kinds of things when you automate them, and it will be very hard to do it by hand if you had to do each plot individually and then save each one by hand. Okay, another thing that we can see now is how to add tests to our modules. It's very useful when you are writing your code to test each function individually, but it's also useful to retain a battery of tests that you can run anytime you change some things to your code. So let's suppose that we wanted to use all these examples as a set of tests to see if everything is working correctly. But we want these tests to be executed if we open our module and run it in Spider, for example, if we actually execute our module. But we don't want the tests to be executed when we import functions from this module into a different module, because then we would be using our toolbox, the functions that we created, and we don't want all the tests to be running at that time. This is easy to do because when you run a module in Python, the main module will have a name called main. So this attribute __ name and then 2 underscores, it's a special attribute that is created on a module, and it's set to the string __ main and then 2 underscores if this is the module that you are executing. For example, you press F5. If it's the module that was imported and it's being executed because it was imported, then the name will be the name of the module, will be the name of the file where the module is stored. So if you do something like this at the end of your module, if you set if the name is equal to main, then the code that you put inside this block will only be executed if you are executing this particular file as the main module. If you are importing this file into some other module, then this code will not be executed. So this is very useful to get some quick tests on your modules inside the module that are not run when you import into some other module. So if we import the Gapminder module, then the name of the module will be Gapminder. But if we run the module, the name will be main. And so we can put all the tests by checking the condition to distinguish whether or not this module is being imported or it's actually being run. And this way, if you are making changes to your module, adding functions, changing anything, you can test everything just by pressing F5 and you run the module and you execute all the tests. If then you are using your module in some other by importing into another module, then the tests are not run, because by that time it's presumed that you already tested everything and you don't need to run the tests every time you use your module. Okay, so to sum up this lecture, we saw some basics of how to use how to do plots with matplotlib and pyplot. We saw these styles, the colors, the simple plots. There are lots of different options and different plots. We are not going to be exhaustive about this, but once you have an idea of how these things work, then it's easy to just check the examples and the documentation and adapt everything to what you want to do. And we saw this general approach where we are separating different tasks in our program. We are loading data into an internal data structure, for example, the dictionaries. This may not be trivial. You may have to think about how you're going to structure the data in your program, but then we load everything that we want into this same format. And then we create our program around this structure, because usually this is the most stable thing in our program, which will be the data that we want to use. We are automating data processing, so it will all be centered on the data, and this will be the most important part of our program. It is the data and how it's structured. So when we want to use that data, we create auxiliary functions that get the data that we need and then do things with that data, computations, plots, save things, and so on. And we also saw how automation can allow us to do things that by hand would be very difficult or very boring to do, like creating animations, lots of images and such. So if you want to take a read at the matplotlib site, you have lots of tutorials, documentation, examples, and so on. You don't need to actually study this in detail, but it's useful to give you an idea of what you can do and where to find the information to do it if you need it. Okay, so I'll just log into to Colibri and I'll see you in the live session on Zoom. Okay, see you soon.